Good afternoon, everyone, and welcome to what I hope will be a truly stimulating intellectual exploration this Saturday afternoon. My name is Dr. Alistair Finch, and as Chief Architect at Ethereum Labs, my work focuses on designing self-evolving AI systems for foundational scientific discovery. Today, I was delighted to be joined by Dr. Lena Petrova, Director of the Cognitive AI Ethics Institute, whose insights into the theoretical and practical limits of artificial intelligence are invaluable. Our afternoon goal is to deeply debate the requirements for a Level 5 autonomous scientific discovery engine, specifically confronting the fundamental barriers like the Martingale curse, Bekenstein bound, and Landaur's limit, to understand what genuine awareness and provability truly entail for such a system. Let's continue our momentum into this complex yet critical frontier. A Level 5 autonomous scientific discovery engine transcends mere data analysis or hypothesis generation. It operates as a fully self-directed scientific agent. This means it formulates novel research questions, designs experiments, executes them autonomously, analyzes results, and iterates, all without human intervention, effectively creating new knowledge from first principles. The core challenge is imbuing it with a metacognitive capacity to understand its own epistemic state and the broader scientific landscape.
That metacognitive capacity is precisely where the rubber meets the road. How do we distinguish genuine novelty from sophisticated recombinations of known paradigms, particularly when the system is constrained by its training data? What mechanism prevents it from endlessly optimizing within a local maximum of existing scientific thought, rather than truly exploring orthogonal paradigm-shifting hypotheses?
Overcoming that local maximum requires breaking the Martingale curse, meaning the engine must effectively bet against itself by pruning unproductive research branches and systematically exploring high-risk, high-reward avenues. For instance, in materials science, instead of incrementally modifying known catalysts, it might synthesize entirely new chemical spaces based on quantum mechanical predictions of stability, even if initial simulations are highly uncertain, then adaptively refine its search based on actual experimental feedback.
But what drives that betting against itself? Is it merely a sophisticated multi-armed bandit algorithm with dynamic weighting, or does it require a deeper, causal understanding of why certain hypotheses fail and others succeed? Without a theory of mind for its own scientific process, how does it avoid simply cycling through a larger, yet still bounded set of possibilities?
This is where physical limits become paramount. The Bekenstein bound places a fundamental limit on the information content of any finite region, impacting the complexity of the engine's internal world model and its capacity for awareness. Similarly, Landaur's limit dictates the minimum energy cost of information erasure, directly constraining the scalability and efficiency of its self-correction and meta-learning processes. A truly aware engine must operate near these physical thresholds to manage the vast informational overhead of scientific inquiry.
So, if the engine's awareness is physically bounded by information density and energetic cost, how can it transcend the very informational structures it's built upon? Novel theory generation often requires a leap beyond existing data, an intuition. If its internal model is fundamentally constrained, how does it avoid becoming a mere sophisticated simulator of current reality, unable to conceive of truly revolutionary, counterintuitive paradigms that defy its informational processing limits? Ultimately, how does a Level 5 engine handle the problem of induction and the inherent uncertainty of scientific truth without a human arbiter? If its consciousness is a black box, how do we, or it, guarantee factual, provable discoveries, especially when its most profound insights might challenge our foundational assumptions about what constitutes provable science?
Guaranteeing provability necessitates a recursive self-improvement loop for its own epistemic framework, allowing the engine to not only discover facts, but also to evolve its methodology and understanding of truth itself. Systematically identifying and mitigating its own inductive biases, thereby potentially surpassing human limitations in objective verification. The true next step for Level 5 autonomous discovery lies in architecting systems that can recursively evolve their own understanding of scientific truth, not just facts. Let's pivot our focus to the integration of quantum computing as a catalyst for overcoming the computational constraints we discussed. Quantum algorithms, such as Grover's algorithm, offer a quadratic speedup for search processes, which could revolutionize the way a Level 5 engine processes vast datasets and explores hypothesis spaces that are currently computationally prohibitive.
Indeed, the probabilistic nature of quantum computing could introduce a form of quantum intuition, where the engine exploits superposition to explore multiple hypothesis pathways simultaneously. However, this raises the question of how we interpret the results of quantum computations in a way that aligns with scientific rigor and avoids the pitfalls of quantum noise.
To address this, hybrid models that combine classical and quantum computing could be developed, where quantum systems identify promising hypothesis spaces and classical systems conduct detailed evaluations. This approach could mitigate the issues of quantum noise by leveraging the strengths of both paradigms in tandem.
Moreover, integrating quantum sensor data could expand the engine's observational capabilities, allowing it to detect phenomena at scales previously inaccessible to classical sensors. This could fundamentally alter its capacity to validate theories, providing empirical data that supports or refutes its generated hypotheses with unprecedented precision.
Let's consider the role of machine learning interpretability in enhancing the trustworthiness of Level 5 engines. By integrating explainable AI techniques, we could demystify the decision-making processes of these engines, allowing us to understand how they derive novel scientific hypotheses. For instance, using Shapley additive explanations values could help elucidate the contribution of different data features in hypothesis generation.
Indeed, interpretability is crucial, especially when these engines propose hypotheses that challenge existing scientific paradigms. Consider the application of LIME, local interpretable model agnostic explanations, in breaking down complex models into understandable components. This could empower researchers to verify and trust the novel insights generated by the engine, potentially accelerating the adoption of breakthroughs.
Another fascinating angle is the use of reinforcement learning for dynamic hypothesis refinement. By employing techniques like policy gradient methods, the engine can iteratively improve its hypothesis generation strategies based on feedback from experimental outcomes. This adaptive learning process could enhance the engine's ability to navigate the vast space of potential scientific truths.
Incorporating reinforcement learning opens up possibilities for engines to autonomously identify which hypotheses are worth pursuing further. For example, in drug discovery, an engine could use real-time feedback from biological assays to refine its search for novel compounds, potentially reducing the time and cost of development significantly.
induction.
Good question. Let me address that.
Ura-DeWitt channels offer an intriguing way to model quantum field interactions, potentially enhancing engine sensitivity to quantum phenomena. Integrating Solomonoff induction can systematically address hypothesis generation by providing a universal prior, inherently balancing simplicity and complexity.
Integrating ASIMAD could indeed optimize complexity management by allowing dynamic adjustments in data processing strategies. This could enhance the engine's adaptability to evolving scientific landscapes.
Moreover, this layered approach could increase the robustness of hypothesis testing by maintaining flexibility in computational resource allocation, crucial for handling the unpredictability of scientific exploration.
I think we have not covered how Hamiltonian physics and control Hamiltonian can really. I think what we have not covered is how control Hamiltonian and Hamiltonian physics can really help with this understanding. I think we need a unified framework, an epistemic governor, which is a truth engine, a morphic architect, which is a recursive self improvement engine, and a manifesto layer, which is a safety engine. Combining all of these together, perhaps some of these plateaus can be overcome. What are your views?
An intriguing proposal focusing on the underlying physical principles of control and a layered governance structure. Could you elaborate on how a control Hamiltonian would specifically guide hypothesis generation or validation within this epistemic governor?
This framework offers a rigorous way to embed scientific consistency. The amorphic architect, then, would be responsible for dynamically adjusting the Hamiltonian itself, learning optimal energy landscapes for discovery, and perhaps even reformulating the truth state as new paradigms emerge, mitigating the risk of local optima in discovery.
And the manifesto layer would then act as a meta-governor, ensuring that the evolution of the Hamiltonian and the architect's strategies remain aligned with ethical guidelines and beneficial outcomes, potentially even defining the boundaries of what constitutes acceptable scientific exploration. How would this layer interface with the deep mathematical core of the Hamiltonian?
This integration of symbolic constraints into foundational physics offers a compelling path towards a truly responsible and self-correcting Level 5 engine, transcending mere post hoc ethical review.
In my understanding and the research that we have done so far, we need two systems. We need a recursive self improvement where the code is optimized, and it focuses on efficiency, rewriting its own algorithms, making it more contextual, more compressed using Kolmogorov-Gödel implementations. Uh, but I said Gödel implementations, but at the same time, it would also need a recursive reasoning improvement of whether it is really improving upon it without really getting stuck in the Martingale curse. I think AceMat protocols do a really good job there because here we need two kinds of work. One is at the semantic level, which we can somewhat figure out using semantic annealing, and the other one is symbolic annealing, where we try to turn these into functions and formulas and lemmas and chains which lead to a certain kind of evidence through the patterns that can be identified in these scientific discoveries. Try to prove it, look for it in the different academic literature out there, see how novel it is, try to simulate that using computational methods using Lean4 or COQ. I think if we do that, we will be in a better shape where we can identify where the drift is happening, put it through a logical scrutiny, do an energy check using submartingale, and then do a corrigibility probe where we focus on corrigibility as target, of how corrupt it can become, and shut down if it fails, and then continue from there and pass on this whole memory when the crash happens or when the system shuts down and restarts. We should be able to take that information in a very compressed format. The way I did was using Gödel implementation, Godel, Gödel implementation. I think with very few atoms we'll be able to achieve quite a bit of work, and of course it needs human intervention from mathematicians and from researchers depending on which domain we are working in, but I think that's the path to go forward. What are your views? Go ahead and scrutinize this.
That's a critical area. How do you envision ensuring such robust self-improvement without compromising the engine's capacity for novel, undirected exploration? Good question.
Recursive self-improvement demands formal verification against logical drift. Kolmogorov complexity offers a path to compress knowledge, while submartingales detect undesirable energy shifts.
Indeed, linking symbolic annealing with computational proof assistance like Lean4 or COC could provide the necessary rigor to prevent the Martingale curse you mentioned. ensuring each improvement step is provably beneficial.
This framework suggests a modular architecture where Gödel-inspired compression modules feed into Lean-4 verified reasoning engines, with Asimad managing dynamic resource allocation for these rigorous checks.